Okay. Hello, everyone. My name is Pavin Virdee, and today I'm going to be talking about silicon-germanium heterojunction bipolar transistors, or in short, SiGe HBTs. This is for EE529 microwave device electronics, and the professor is Dr. Dennis Derrickson, and again, my name is Pavin Singh Virdee. So first, I'm going to begin by kind of outlining what I'm going to be talking about today. I'm going to start off with a brief introduction of silicon-germanium HBTs, and then I'm going to get a little bit into the general background and theory of BJTs before moving into SiGe HBTs. The reason I chose to do that is simply because the circuit operation of silicon-germanium HBTs and HBTs in general is actually very similar, if not exactly the same as traditional BJTs, but when you get down into a band diagram level, that's where kind of the differences take prevalence, and that's where these enhanced performance features actually can come to play. Next, I'm going to be talking about some applications of SiGe HBTs, and that's kind of one of my favorite parts, just because I'm using them very avidly right now in my master's thesis, as well previously in my senior design project. And then I'm going to kind of wrap it up with some summary. I've included my references for this presentation as well at the end. So to give a brief introduction on silicon-germanium heterojunction bipolar transistors, they were developed initially in around the 1990s by IBM Research and Technologies. And essentially, like I had already mentioned, the circuit operation of an HBT matches that of a traditional BJT in the sense of they really operate as current-controlled devices. So like we all know, a transistor is a nonlinear semiconductor device that can be used for a variety of applications. And these days, you can find BJTs, MOSFETs, or any type of transistor, moreover, in any type of electronic device, really. And there's hundreds to thousands to even millions of these devices and products. They have purposes of amplification, rectification, switching purposes for high frequency, high power, low power, digital, analog, everything. Like I mentioned, they're current controlled devices. And the way that I actually like to think about BJTs and HBTs in particular is that they're current controlled resistors. That is, as we vary the base current, the actual collector emitter current flowing through that transistor itself is actually going to increase or decrease. So what we're really doing is just as we're increasing the base current, we're changing the impedance of the collector to emitter terminals, hence changing the essentially the equivalent current that's flowing through them. HBTs, SiGe HBTs specifically, are most commonly seen in RF and microwave applications due to their increased frequency response. They have really good transition frequencies as well as low noise capabilities, gain, linearity. I'll get into that in a little bit, but really some of the biggest features of HBTs, SiGe HBTs in particular, is that it features a wide bandgap emitter and also a low bandgap base, and that base region is also heavily doped. And that's really one point that I'm really going to hone in on, is the heavily doped base region, because that is one of the really key parts that makes this device so great, really. And like I mentioned, there's a variety of applications from R&D to test. While I was at Keysight Technologies, they use SiGe HBTs. Aerospace, the company I'm currently at, Astranis, abundance of different types of technologies, consumer electronics. They can be used for oscillators, amplifiers, switches, power regulation circuits, everything you can kind of think of. So now a little bit of background on the BJT before I get into the HBT. So like I mentioned, it is a current control device. So what that means is this base inputting base current actually controls the amount of collector emitter current that is flowing. And as you can see when I'm pointing out with figure 1 is a NPN BJT type. NPN refers to the collector is an N-type, base is P-type, while the emitter is N-type as well. Alternatively, there are PNP transistors where it actually goes P-type, N-type, P-type. And like I mentioned, the base plus the collector currents are actually, the sum of those two currents are actually equal to the emitter current. But one thing to note that is if our beta term of our transistor, or essentially our current gain from the base to the collector, is sufficiently high, then in the grand scheme of things, when we're actually calculating these DC biasing currents, we can really just neglect that base current and kind of think of the collector current being equal to this emitter current. At a very low level, a BJT transistor and HBT is really just composed of two PN diodes. So in an NPN, you're going to have two PN diodes being forward biased facing towards the base, from the base facing towards the collector, and from the base going down towards the emitter. So the direction of this arrow is actually the direction of that diode going downward, with the same diode actually anode at the base, cathode at the collector. And like I mentioned, there's an associated current gain from the base to the collector, and that is actually what allows for the amplification in signals. And kind of what I'm mentioning earlier too about how this base current is actually going to change and vary and control our collector emitter current is shown here in figure 2. And what figure 2 is showing is basically no matter the collector emitter voltage, independent of that, as we're changing once we get into this saturation kind of forward active region, as we change this collector emitter voltage, that has no influence actually on the current that's actually flowing from the collector node to the emitter node. That is truly just controlled by the base current. So as we see, as we increase that base current, the amount of current that's going to be able to flow through that collector is also increasing as well. So another note is that generally, if we say we have a common emitter, what that means is if the emitter is grounded, we're taking our input going into the base, output at the collector. We can even ground the collector and say we want to take the output at the base as well. BJTs are, one good feature about them is they generally have a high input impedance at the base. And alternatively, they have a low output collector or emitter impedance. And this is actually really good for amplifier applications where you want a really high input impedance and you want a low output impedance so that your loading effects on your amplifier aren't going to be swinging your amplifier performance too much. Another thing to mention is BJTs. The majority carrier in an NPN is electrons, while the majority carrier for current in a PNP is actually holes. So that's one thing that BJTs and HBTs differ from MOSFETs is you have, usually you have an N-type or a P-type MOSFET. And with a BJT, it's actually a combination of P-type and N-type. And the final thing I wanted to mention is NPN, HBTs, and BJTs are actually more common than PNPs because N-type substrates actually have the ability to allow electron holes to transport faster in them than P-type substrates. And this is particularly useful in switching applications. And in the frequency domain, it actually translates to higher transition frequencies. So now moving into the Silicon-Germanium HBT, now that we have a little bit of a background. So like I mentioned, in this BJT, right, we're going to have usually an NPN. It's either silicon-based, it can be germanium-based, a semiconductor material, but it's a homojunction in the sense that all three regions are actually the same semiconductor material. So now what we're doing with an HBT, silicon-germanium specifically, is we're actually going to be deferring the base region semiconductor with the emitter region semiconductor. And what that's going to create really is a heterojunction. And what this heterojunction is going to allow us to do is a number of things. But essentially, when we evaluate the band diagram, it's going to really help us with band offsetting to help with current injection, electron injection specifically. So how the SiGe structural diagram is kind of composed is essentially sandwiching a SiGe, silicon-germanium material base between two silicon emitters and collectors. And on the right-hand side, figure 3, it is an NPN. So we have an N-type silicon semiconductor emitter, a P-type base, which is SiGe, and then we have our collector, which is also an N-type silicon based. One actually key characteristic also about the emitter region is that in silicon-germanium HBTs is they have a wide band gap emitter. It's kind of what I mentioned earlier. And alternatively, they have a low band gap base. And what this allows us to do is actually kind of optimize and kind of vary and change our band offsets, our Fermi levels, as well as our conduction valence band offsets, such that we can actually optimize these offsets to limit hole injection and maximize electron injection, specifically diffusion, which is going to be the main majority carrier in an NPN for electrons. The main kind of current type is diffusion current. And another really, really key takeaway that I mentioned earlier is the base region is very heavily doped. And what that means is it kind of has two really key takeaways, which kind of go hand in hand. The biggest key takeaway is by heavily doping this base region, what we can actually achieve is a decreased base ohmic resistance. So that means that the equivalent ohmic resistance of this base region is going to be decreased since we have a higher doping profile in the base, which is the silicon-germanium portion. And what that translates to is actually a decreased thermal noise generation, because as we remember in some of our previous courses, decreasing your resistance will actually decrease your noise generation, thermal noise generation specifically. So now we're going to evaluate kind of a band diagram. So right here on the right, figure 4, what we have is a band diagram for SiGe specifically. And I want to note that the dash, this operation is a forward active biased NPN specifically, where we have the emitter silicon, we have the P-type silicon-germanium base, and we have the N-type silicon collector. And on the bottom right, we see here where my cursor is, laser pointer, is we can actually evaluate kind of the doping profile. And one key takeaway here is see how it's kind of a linearly doping. So what that means is that the doping in this base profile, yes, it is heavily doped, but the way that we move from the emitter to the base is actually a graded doping. And what this graded doping actually allows us to do is two things. Well, one thing, the main thing is the graded doping allows decreased base electron transport time. So what that means is essentially the ability for electrons/holes to move and transport to and from and within the base is actually decreased. And essentially they're able to move faster. And what this does is it actually increases the transition frequency, aka our performance. And it allows us to essentially get better high frequency performance. And the next thing I want to point out is, well, one thing in general with the HBT is similar to the BJT, is holes in an NPM specifically, electrons are going to be emitted from the emitter. They're going to diffuse into the base, and then they're going to fuse down and be collected into the collector. So for an NPN, emitters or electrons are our majority carrier, and those are being emitted from the emitter and diffused and collected in the collector. Alternatively, if we have a PNP, what's going to happen is the majority carrier switches to holes, right? So then the holes are going to be emitted in the emitter. They're going to be diffusing across into the collector. And similarly, for an NPN here, the whole diffusion right here is what I'm talking about. As you can see right here, this H plus is going to be moving down from this base portion down into the emitter. This is actually going to be diffusing across the base into the emitter right here as this point states. So the next thing I want to talk about is right here on the right-hand side. I actually want to do a little bit of comparing and contrasting between the SiGe HBT and purely Silicon BJT. So the solid lines are actually going to be represented by the HBT, whereas the dashed lines are going to be represented by our a traditional Silicon BJT. So one of the biggest things here, well, there's two really key takeaways here. One is, or observations rather, is note that the Fermi levels are all equivalent. So what I said on a couple slides ago actually is optimize band offset. The wide band gap emitter with the low band gap base allows us to optimize our band offset. This is exactly what's happening. So if you're noticing, we have a lower band gap base portion while we still are having a wide band gap emitter. And that allows for the Fermi levels to be lined up. And that basically does. And we can also notice how the conduction band right here, the barrier, is actually decreased compared to the silicon. So what that translates to is at a particular biasing level, it takes less energy for these electrons to actually diffuse all the way over into the base and then down into the collector. So if this barrier is decreased, so what that means is at a lower biasing level, we can actually achieve an increased current, increased collector to emitter current. And the other thing I wanted to mention is the base valence band is also similar in both the silicon and the Silicon-Germanium HBT compared to the BJT. So what that means is basically the whole flow that's going to be diffusing from the base to the emitter is going to be about the same, and just really that change is going to be negligible. So kind of the key takeaway from here is that at the same biasing level for a BJT and an HBT, we can actually achieve a higher essentially collector to emitter current because of this conduction band being decreased. And essentially that means that the electrons that are going to be diffusing from the emitter all the way to the collector require less energy, and they can do so faster, quicker, and at less biasing levels. Also with minimized noise generation as well. So I'm going to get into a little bit of SiGe HBT performance, some of the features specifically. So everything that I've kind of been talking about of decreasing that conduction band, lining up those Fermi levels, that allows us, and then the graded doping of the base as well as the heavy doping of the base allows us to do kind of really two main things. Is one is we're going to increase our transition frequency, and then two is we're going to optimize our low noise performance of this device. So transition frequency, for those unfamiliar, is essentially the current gain bandwidth product of a transistor. Is a really, really key frequency parameter of a transistor. And it is essentially the point within a transistor where you is the frequency at which you're having zero current gain, or a current gain of unity actually. So this increased transition time also translates to faster switching times in the time domain if we want to be using HBTs for switches. And one thing is figure 6 shows that I found very fascinating is from the 1980s all the way kind of up to the early 1990s with the invention of the SiGe HBT by IBM in 1990. This is kind of the trend, the historical trend of transition frequency, the peak transition frequency of these silicon devices. And we can see it's kind of, maxing out maybe around 40 gigahertz. And then 1990 comes around with the SiGe, and we're able to achieve up into millimeter wave frequency. I mean, maybe around 75 gigahertz. So this is a huge advancement and huge capability for us to be able to have that higher transition frequency to get more gain, higher bandwidth, more frequency operation, and just an abundance of performance features, faster switching time. Also, I wanted to mention is the low noise capabilities. So while maintaining that gain and switching performance with the decreased biasing levels, like I mentioned earlier, because we don't need as much biasing current to be able to achieve the same collector current or even higher collector current due to that conduction band decrease and the band offsetting. That actually allows for decrease in noise generation, because higher doping of the base, there's two things. Higher doping of the base will allow for a decreased ohmic resistance of the base, therefore decreased thermal generation of noise, like thermal noise generation. And then also decreased biasing levels will actually decrease the shot noise in the transistor, because shot noise is actually proportional to biasing current and of our transistor, and specifically collector current. So as that collector current increases, the shot noise will also increase. So if we're able to achieve higher performance at decreased biasing levels and current levels, then we can actually be able to not only minimize thermal noise, but also minimize shot noise, which is really, really key. So now I want to kind of get into some applications of SiGe HBTs. One huge application is amplifiers, and figure 7 here shows actually a cascode type low noise amplifier. This was actually from my senior design project last year that I did, and it's featuring an Infineon Silicon-Germanium NPN type HBT, specifically their BFP 740 series. So a little bit about this topology, about the circuit. It's a cascode type low noise amplifier. It's being biased in a class A operation. So what class A means is that these transistors are always going to be on, and the full waveform is going to be conducting as well as being amplified. So we have a classic biasing scheme here for a cascode, and one feature of a cascode amplifier here is what we have here is the first transistor, Q2, you can see right here. It's actually a common emitter, and then the output of that is actually getting fed into the emitter of the second transistor, Q1, and that topology is a common base. So the output there is taking in the collector. So what that allows us to do, what both of these combined allows us to do, is actually mitigate the Miller effect. And the Miller effect is essentially the parasitic capacitance between the base terminal and the collector terminal. And by sticking another transistor in between the base and the collector of Q2, we actually are able to mitigate the Miller effect entirely. And the Miller effect, what that parasitic capacitance will do is it'll actually short out your gain and decrease your gain at high frequencies. So that's why that cascode topology is chosen here. But the SiGe HBT allows us to really get some really good performance out of this. We were able to achieve 21 dBs of gain, 0.78 dBs of noise figure at 3.8 gigahertz, which was pretty good performance, as well as high linearity of 24 dBm at the output third order intercept. And obviously there was a little bit of fancy matching here with some shunt radial stubs here, but the SiGe HBT definitely did help contribute to that. Next application is an oscillator, and this one I really want to highlight because this is my master's thesis design project, or it's part of it, is designing a phase lock loop frequency synthesizer, specifically where the SiGe HBTs are coming into play is with the voltage controlled oscillator. So figure 8 here on the right-hand side shows a LC differential topology VCO. And these HBTs are also Infineon SiGe HBTs, different transistor type. It's the BFR 740 L3RH, if you're interested. Has a really high transition frequency of 42 gigahertz, which is pretty significant, with a max power gain of 35 decibels, which is really good. And And one thing to note is 35 dBs is acquired at only 15 milliamps of collector current, with corresponding only half a dB of potentially the lowest noise figure possible, with really high linearity specs above 20 dBm as well. So this type of application, very briefly, but how this circuit works is we essentially have a differential pair on the bottom, and up at the top, we have an LC tank circuit. At the top, the LC tank kind of serves as our frequency selector circuit, whereas the bottom kind of serves as our actual oscillator and our feedback. So as we can see, the input of Q1 is actually the output of Q2, and the input of Q2 is the output of Q1. So if we think about this in like a block diagram, it's essentially just two amplifiers cascaded in series with constant feedback. And since each common emitter itself is inverting, what that means is we can achieve 180 degrees here, 180 degrees here. The full closed loop phase is going to be equal to 360 degrees, which is positive feedback, as we know. And since it's two common emitter type amplifiers, if we bias them properly with our super high transition frequency and max power gain of our handy dandy SiGe HBTs, we'll be able to achieve a high gain greater than 1. And as we know, a gain greater than 1 with 2 pi, integer 2 pi phase differences in the closed loop is our necessary oscillation conditions. And the way that this actually circuit works as a VCO is these capacitors are actually not fixed capacitors. They're actually varactor diodes. And what varactor diodes are is essentially reverse bias diodes. And as we change the reverse bias voltage across them, so in this case, it would be V-tune, we can actually control these varactor diodes act as voltage controlled capacitors. So as we can tune that capacitance, we can actually tune our frequency selection. Hence, we have a LC tank that is actually frequency tunable, really. So that's about it. What I wanted to talk about. So I kind of wanted to summarize what I've kind of highlighted here, and some key takeaways is the SiGe HBT features, as we've mentioned, the emitter base is the heterostructure, where the base is that SiGe component, and the emitter is the actual silicon component itself. The base features linearly, not linearly, but uniformly graded doping, which is highly doped, and that actually allows us to decrease the ohmic resistance and alternatively increase our base electron transport, which, as we know, decreases noise generation as well as increases gain. And those two are also achievable by the band offsetting, which actually allows for a higher collector emitter majority current to actually diffuse through from the emitter all the way to the collector, with similar biasing conditions of that of a BJT silicon, like a Silicon BJT. We also know that SiGe HBTs feature increased frequency responses and transition frequencies, and that makes them very desirable for RF and microwave applications, such as amplifiers like my LNA, oscillators like my frequency synthesizer, and many more types of applications. So, final thing I wanted to wrap up with my references. I had a couple references for my BJT, as well as two really good texts that actually specifically just focus on SiGe HBTs. The entire books are just those, as well as some Infineon data sheets, as well as a NASA application note. So that concludes my presentation on Silicon-Germanium HBTs. And I would like to thank everyone for their time. And once again, my name is Pavin Virdee, and thank you. I hope you've all enjoyed this presentation.